Hello, hello, hello. So we're moving on to chapter 10, and this gets me pretty excited because I actually adore nonlinear ODEs. This is really one of my passions when it comes to mathematics. It's just like nonlinear dynamics in general. They fascinate me, and I spend a lot of my free time trying to figure out some new properties of these. So I'm really excited to be talking about these. This is part 3 of the book. In some ways, we exhausted at least what I wanted to cover for linear ODEs and linear maps for this book. And so now we're on section 3, or part 3, I guess, of the book, which is nonlinear. And I'm starting this out very similarly to how I started the linear section, just so that we can be reinforced about what it would mean to be nonlinear versus linear. And hopefully this way you take that perspective into if you're ever going to be working with differential equations. In the future, you can recognize immediately if the differential equation is linear or nonlinear, because it means a lot of different things. You would approach a linear problem completely differently than a nonlinear problem. So we'll just reinforce our nonlinear functions and maps, basically as, not the linear functions or maps. So start with the question, how would we define it? And we're just going to say it's the ones that are not linear. But let's look at the definition. Okay, so we're going to consider a vector algebra, actually, and a vector algebra is like a vector space with multiplication of vectors as well. So something like, let's grab analytic functions, for example. Analytic functions, I can't remember my notation perfectly, but I think I said something like x naught, analytic function centered at x naught. I can take an analytic function f centered at x naught and add that to an analytic function g with some linear combination, and I get h. That's a vector space. Everybody feels good about that. Well, what makes it a vector algebra is that if I take an analytic function f and multiply it by an analytic function g, this is also an analytic function, call it phi of x, right? So we can also multiply analytic functions as well as add them together and perform scalar multiplication, and we remain in the space. So that's an algebra, and that's going to be important for nonlinear maps because they're going to be constructed basically via this multiplication in the algebra. Well, anyway, it's any function that does not satisfy linearity. And we'll recall that this is the definition of linearity if I had an equal sign in the middle, but here I have a not equal sign, right? So if there's at least one spot in the domain, if you put those vectors into the domain of n, and you don't get the linearity property out, then it's a nonlinear function. And so that's pretty easy to interpret. I'm going to use a capital N in this section for nonlinear. It's a little bit standard notation. Most references would just use F for nonlinear maps because they are functions. But I'm going to use capital N because I really want to stress that this is kind of like an operator, and it's kind of like a nonlinear operator. So operator, capital letter, nonlinear, capital N. My linear operators were L's. So that's what I'm going to use in this section. So if you see an N, think nonlinear map. Let's look at some examples here. So this was really stressed really strongly, and the linear section is that our favorite function that we used to call linear in high school, and even I suppose most of our undergraduate time is not a linear. It's not a linear function. We call the affine function, and it's definitely nonlinear because if I take a linear combination in the domain and I actually compute this, I get a m1 x1, a1 m x1, a2 m x2, and then b, just a single b on the end. But if I decide to compute with an a1 and an a2 on the outside of f and actually go through the work, that the m1 x1s, or you know what I'm trying to say, those terms agree, but the b does not, right? So a1 and a2, if a1 and a2 are 0, then we're definitely not going to get something like that. That's another quick way to check. A very easy way to check. Check if fails. I should say possibly fails. Linearity is what does it map to 0 to? All linear maps map 0 to 0, but a nonlinear map, if I take a map and I put 0 and then I get something that's non-zero, then immediately I know it's nonlinear. So that's an easy way to check. You can't guarantee that though, because something like x squared is nonlinear, but it still maps 0 to 0, which is our next line here. So f of x equals x squared is nonlinear. I think we all know this in our hearts, otherwise life would be way too easy. Because if we just square it, we get all sorts of a2 squareds, which there would be no a1 and a2 squared if it were linear. So there you go. All right, let's see what else. We have the square root function is nonlinear, the exponential function is log is nonlinear. I mean, you know this. The only functions that are linear are multiplication by m, right? F equals mx is the only linear function of one variable. Yeah, and I put that in a remark there. So it should be clear that linear is an extremely strong condition. Most of the functions we interact with are nonlinear. So we provide some examples about how much harder it is to invert nonlinear functions than linear functions. If I look at the constant function, which is nonlinear, and I decide to solve that equation equal to 0, then that's basically me saying, hey, what are the values of x that I would plug into f to get 0? And it's any number if a is 0, but it's no number if a is non-zero, right? This is harkening back to our whole, like, any numerical equation takes the form f of, I was using g at the time, g of x equals 0, and is solved by the pre-image of the set containing 0, right? So any x in the pre-image of the set containing 0 is the solution. I think you should remember back to those days when we were talking about solutions of equations, period. We're harkening back to that there. So we're really looking at pre-images here. And when we have an affine function, yeah, things are pretty easy, right? So an affine function is super easy to solve. This, you'll recall, is in fact a linear equation. The function was not linear, but the equation, when I set it equal to 0, is linear. And that's very easy to solve. Linear equations are basically our favorite equations to solve. And I put a 1 divided by 1 there for very specific reasons. Negative 1 divided by 1b over a. Because as I jump down to maybe solving a quadratic, we have our quadratic formula, which is negative 1/2 b over a is the leading term. And then the cubic formula, look, I actually put it on there. Negative 1/3 b over a as the leading term, and then we get some considerably more complicated terms. But go ahead and reference this if for some strange reason you ever do need the cubic formula for you. And keep in mind that these cube roots right here and here are actually multi-valued in the complex sense. Okay, so they incorporate all cube powers or cube roots of 1 of unity, which are like on the complex unit circle they look like 1 is a cube root, but also this one and this one are the 2 cube roots of unity. So you do actually have 3 solutions here, the same way that the plus or minus right there gives you 2 solutions, right? We should expect 3 solutions here. And for the quartic formula, the leading term is in fact negative 1/4 b over a, but then it gets huge, enormous, right? So we don't include the rest of the quartic formula here. And the quintic formula, most of you perhaps already know this. There's the remark, there's no formula so long as we're restricting ourselves to these so-called elementary operations, plus, minus, times, division, and powers, even logarithms, I think. But you can gain a solution if you define the Bring radical, which is the unique real solution to the 5th power plus x plus a equals 0. Then all of a sudden you do actually have a formula. Not that it's pretty, but just something fun to know. But anyway, this is what I'm trying to stress is that inversion, right? So what's happening here? This is this, and then this one, which is too big to even fit on the screen. Function inversion, nonlinear function inversion, gets tricky, huge, and often impossible very quickly. So like in many cases, you cannot invert a nonlinear function. The quintic, right? So some ax to the 5th plus bx to the 4th and so on. That formula is not that hard to write down, and yet inverting it is impossible without this really funky extra term that we call the Bring radical. That itself would be really impossible not impossible, but it would be difficult to estimate, right? Like it's hard. For a equals 11 or something, this would just like have to be numerically evaluated. We don't have a nice formula for finding that. So very quickly, nonlinear function inversion is just like impossible. And I think everybody's already seen how even when it came to the linear situations, linear function inversion was solved with linear algebra. If I have mx, a capital M plus b as a vector, I can solve that pretty easily with linear algebra. We push ourselves into linear differential equations and things already get considerably more difficult. And now we're headed into nonlinear differential equations. So we're thinking about trying to solve a differential equation where even if it weren't differential, I have to have a formula that's this big to solve it in the cubic setting. And so you can imagine that some of these differential equations are just out of this world, impossible to provide any sort of closed form solution to. But that's not to say that we can't do it sometimes. That's not to say that we don't have other techniques, right? We're only 2/3 the way through the course right now. Clearly, there's a lot for me to say about nonlinear ODEs. It's just that we can't expect to be able to invert them or to be able to solve them in some sort of beautiful sense. Things get a little bit nitty and gritty at this point. Or we just have to make more general statements about the differential equations. Cute little remark here, I say, speaking of nonlinear function inversion, so the Riemann hypothesis that that you've all probably heard a lot about, is just a nonlinear function inversion problem, or a nonlinear solution problem. All we're asking is, what is the preimage of 0? Set minus 3 aligned. But what is the preimage of 0 of the zeta function? If we knew that, then you win $1 million. But for very obvious reasons, nobody knows exactly what that preimage is. So yeah, nonlinear function inversion is kind of at the cutting edge of all mathematics. Everything most mathematicians try to do, certainly the applied ones, is figure out some sort of function inversion for nonlinear functions, because it is just so difficult in many situations. Okay, so that was all very motivational, hypothetical. I just wanted to be like, hey, nonlinear equations are hard. Now let's actually get into what it would mean to solve some, maybe what's the background knowledge we need to solve some differential equations. Because in the linear setting, the background knowledge was in linear operators. In the nonlinear setting, we have to have some background knowledge in nonlinear operators. And then we'll start to see maybe how we can play around with them to start to solve our differential equations. So a nonlinear operator is just going to be a nonlinear function from a vector algebra to itself, which is also a function space, right? So for example, right here, this is a really good one. So if we have a function space, the analytic functions was a great example, centered at x0, I can consider the nonlinear operator n sub g, which just gets defined by composition. It's just going to be the function g of f of x. That's still an analytic function centered at x0. It could be. And yet, if g is nonlinear as a function, this operator itself, which is mapping f now to a new analytic function, will also be a nonlinear map. And the next example is just that the composition of a nonlinear and a linear map is a nonlinear, right? Once you go into this space of nonlinear functions, you can never come back unless you get really lucky, right? You have something like n inverse n of L, right? That would give you L, and then you're linear. But if you just have a single nonlinear and a single linear, then you're stuck at nonlinear, because the inverse of a linear map will always be a linear map. Maybe I should have left that somewhere around. I think it might have been in your linear map section. L inverse of linear is linear. So that's something good to know, right? We can play around in the linear world as much as we want with inversions and everything, but once we head into the nonlinear world, we're stuck. Okay, so we're going to take an aside to talk about these things called K multilinear operators, or in other words, just a lot of people just call this multilinear operators. There is people will call it sometimes multilinear algebra. This is not a very common word to use. I like the term. I think it's a fantastic term to say it's the algebra of multilinear operators, but most people don't use it. So it's something you can say. Multilinear operator is very true. Multilinear algebra, not so much. But there are some books out there that do use the terms. So we're going to define these things called multilinear operators. So a multilinear operator, and there I said K, so if I put a 2 in front of it, a 2 multilinear operator, this number or this number describes the number of inputs. So it's saying K multilinear operators have K inputs, a 2 multilinear operator has 2 inputs, and that's why you'll see here I use the term, the capital letter B, V cross V into V. So it's taking the Cartesian product of 2 vector spaces and then mapping it into that original vector space. And I use the capital B to stand for bilinear, and this is something we do also use a lot, is a bilinear operator is the same as 2 multilinear. And it has 2, so because it maps V cross V into V, that's something like B of U V equals W, right? That's the idea. I'm able to take 2 vectors in and I output 1 vector. And it means the definition of bilinear is the following. If I look here, what this is telling me is it actually says fix the second entry. So in this case, the second entry is V1. So fix that vector V1 in the second entry. Don't do anything with it. Then I have a linear operator. Then my operator is linear in the first entry. And what that means is that here I've taken a linear combination. I'm now that I've fixed V1, pretend like V1's not there. I don't know if there's an easy way for you to pretend that V1's not there, but pretend that V1 is not there on the left or the right. Somehow like make it disappear from your mind. And what it looks like is that B behaves linearly, right? It distributes over the plus sign and it commutes with the multiples. So it distributes over the plus and you get A, B of U1 plus B, B of U2. That's exactly linearity. But it turns out V1 sat along for the ride. So that's what it means to be bilinear. And actually, it's also vice versa, you need to satisfy both. This is exactly the opposite, where now I'm fixing u1. So imagine u1 doesn't exist. Pretend like what I've just put in cyan doesn't exist. Then I have this behavior of b being linear in its second components. It distributes across the plus sign and commutes with the scalars, which happen to be sitting on v2 in this case, right? So bilinear just means, hey, I'm linear in the first component. If I fix the second component, hey, I'm linear in the second component if I fix the first component. And this basically paves the way to the multilinear operators. And I know this notation is a little bit ugly, but what I'm saying is, hey, n, a k multilinear operator, which I'm just calling n, takes k copies of a vector, or k elements of a vector space. And so you can imagine this is like k units long. There's k entries in there. But suppose that at least one of the entries has some linear combination in it. Then what I'm allowed to do is pretend like the operator only on the linear combination, right? Everything else stays fixed, but the operator only on that linear combination term is still linear, right? So I'm linear in every single place that I can put something inside of, but that doesn't make me linear overall, right? It would only make me linear if k here were equal to 1, and I only had one possible input that I could give my operator. So that's what k multilinear means. And we can look at some examples because this really makes it a bit clearer what's going on with multilinear operators. Let's just take multiplication as an example. B of x, y, these are real numbers, right? It's a multilinear operator on the vector algebra, right? The R is a vector algebra. You can add two elements, you can scale them, and you can also multiply two of them. So R is a vector algebra. It's going to take two elements in. It's going to output one element as just the product of the two. And let's see that it's actually multilinear by taking a linear combination of the first entry. If I take a linear combination of the first entry, I've kept the second entry the same, which is y, but the linear combination of the first entry, and then I multiply it by y, well, what do I know about multiplication? That y can distribute over here, so this is actually a x1.y, b x2.y, but these pieces individually, the multiplications there, are the definitions of the bilinear operator, and so there's bilinearity in the first component, or linearity in the first component. I can do the same thing with the second component and gain linearity there, and that's what it means to be bilinear. Similarly, if I decide to grab k real numbers, that's going to be a k multilinear operator, right? If I just go x1 to xk, those are all inputs on the rk cross rk cross rk, or sorry, r cross r cross r k times. And then, right, it's just multiplication of those. That happens to be a k multilinear operator, because if I restrict myself to just one of the entries in k is a linear combination, then that entry is kind of treated separate from the rest of them, right? The rest of them are still just multiplied in some product. But the specific entry, which is a linear combination, sits out front, and we know that the linear combination has a nice distributive property of that product. And so we gain, and the A's come out front, the B comes out front. And if we look at these terms separately, without the A and the B, each of those terms is individually n on all of those pieces, right? So n on all of the pieces, and so we have multilinearity. The next remark's really important. I'm saying these are the canonical examples. Canonical as in like the ones you should always think of. So these are the examples you should think of with multilinear. It's just like multiplication of that many terms. A bilinear operator, multiplication of two terms. K multilinear operator, multiplication of k terms. Okay, so that's like, that should be your intuition with these operators is, hey, how many multiplications are occurring? And if it's, 6 multiplications are occurring, that's a k minus 1. It's 6 minus 1, 5 linear operator, because here in a bilinear, 2 linear operator, there's only 1 multiplication occurring. In a k linear operator, there's only k multiplications occurring because it's the ones between all of the entries. So that's how you can tell the degree of multilinearity, so to speak. So providing the next example, then we have something like multiplication. So here's an operator on two functions. I'm going to multiply the two functions, but I'm also including a derivative on the function on the right. Right? So I'm multiplying both of them, but the function on the right gains a derivative. And this is still going to be bilinear because there's only one multiplication happening. The derivative is not a multiplication. Overall, there's only one multiplication. That gives me a bilinear operator. And we can prove that just directly by checking on some linearity properties of each term. If I jump down, I have an example of something that's not multilinear because I have a multiplication here. So that term by itself would be bilinear. But if I decide that my nonlinear operator needs to add f prime onto things, then that switches things, right? Because there's no multiplication on the f prime term. And when there's no multiplication on the f prime term, that can't be bilinear. And if I'm adding two nonlinear functions together, they would need to be Actually, I don't think you can even add two bilinear functions together and get something that's bilinear. So you need to just be careful that the multiplication of multilinear operators occurs in one big term, but the instant I decide to add a new operator on there, then I'm going to lose multilinearity. But I'm still nonlinear, right? It's really hard to stop being nonlinear. The next theorem is very important. The next theorem is our version of matrices, but for bilinear operators. Remember, in matrices, with a linear operator L, there was a matrix. There exists a matrix L, M, N, indexed by N and M. Right? Interpret that as a matrix, which represents L with respect to a basis. Right, so once we have a basis and a linear operator, we were able to construct a matrix. I watched you all do this in the exercises. We can do the same thing with a bilinear operator. We're just not getting a matrix. Okay, that's the important thing to say. We can do the same thing for bilinear B, bilinear, but it's not a matrix. So that's what we want to be careful of, is this is no longer going to behave like a matrix, it's just going to behave like this representation. So here we are, I'm defining it as, recall it was L sub nm was my matrix, because a matrix has a row and a column. Now this one has a row, it has a column, and it has some sort of depth to it. Okay, so we're thinking about L as like this is a three-dimensional matrix in some sense. You can call it an array, you can call it a tensor if you want to. There's all sorts of names you can give this sort of mathematical object, which is indexed by three numbers. But we compute it with the following, right? So this is the same computation as we had before. It was the image, it's the image of the first however many entries, inner product with the very last entry. So this is the same definition we had before. And in fact, given this representation, now if we represent an element of my vector algebra F as its sum against the basis, and G as its sum against the basis, then we can compute the bilinear operator against F and G as the sum over now three entries of B, N, M, L, A, N, B, M. So it's the two vectors F and G have been interpreted against B, and then I sum against my bases. So we want to think about this. This is harkening back to the matrix version. We had N, M, and this was just L of, it says L, N, M, A, N, E sub M, or I might have those indices backwards or something like that. But that's the way it was with a matrix, because L, the linear operator, only had one input. Right? And so we were able to get away with this only having one input, the matrix, and then the second entry in the matrix had to reconstruct ourselves against the basis. Well, here, because B has two inputs, we're required that the representation also has two inputs. And those two inputs have to get summed over, and then we're allowed to sum over the basis elements. So it's just we're stepping up in the total number of indexing. We step up in the total number of indexing that I need on my operator to represent it with respect to a basis. And there's a proof there, so you can verify that this is how we would construct it. We can do the same thing with a k multilinear operator. The notation gets horrendous because I have to talk about a bunch of it's multiplications of all of the vector representations of each of the f's which are being input into n, right? And this is actually heuristically, this is why we can think of every k multilinear operator as a multiplication of k elements, because what's happening right there is literally a multiplication. That's multiplication of the scalar field that f is represented by, and so we get multiplication of the scalar field as well as some extra array that has very many entries to it. But yeah, we can keep jumping up in basically as many multilinears as we want, and we just have to represent them as it's the image of distinct basis elements interproducted with yet one more basis element. So it's a lot of work to go through all of it, but you do get a nice representation, which is useful for the same reason matrices were useful, is that computers really like to see these representations. You can get much farther considering multilinear operators with a computer if you represent them like this rather than just as the operator themselves. I've got a remark about tensors. If anyone is familiar with tensors and the Einstein summation convention, you can represent these a little bit more cleverly. But if you're not familiar with that, then I wouldn't worry about it. So the next thing we're going to talk about is basically that multilinear operators are great, but what we actually care about when it comes to differential equations are these things called monomials. Because, for example, a generic nonlinear differential equation would be something like d dt of y equals y squared. The right-hand side there is not, this is not a bilinear operator, even though there's a single multiplication there. This is a kind of like, it's like the bilinear operator of f and g, which equals f times g, but it's evaluated with both entries being the same, right? The entry f and the entry g are the same, and then that gives me y squared out of it. So this is what I call a derived monomial, and this is not a very common definition, actually. I don't know what these are called in traditional senses, but it's a monomial because it's really a kth power, right? It's a degree k map, but it's a map from v to itself, right? I don't need k powers of v. N as a multilinear operator needs k powers of v, but n sub k, which I'm calling the derived monomial, only needs an input of one copy of v, and it's defined as the multilinear operator, but every entry is the same, right? So these monomials, I'll say derived monomials, are k multilinear operators, but every entry is the same. So I'm plugging the same vector into every single entry, and that's why I really only need one input, right? There's only one vector that's getting input into this, and that's why my domain is just v and not v to a higher power. And so yeah, the next example is the one I was referring to. If I talk about the square, this is the squaring operation, right? So if I take a function and I want to square it, that's a derived monomial of degree 2, also known as a quadratic, right? So if I square a number, that's a monomial. It only has one input. Even though the bilinear form or the bilinear operator is f times g, I'm plugging f in for both entries to get f squared. Okay, so what follows from this is the nonlinear operators that we consider in this book. Okay, we now define the nonlinear operators we consider in the book. There are many other nonlinear operators than the ones we're going to consider, but we're going to consider these because these are the ones that show up in a lot of physical systems. They're also the ones that we have a little bit more ability to make predictions about or make statements about. These are called the analytic operators. So an analytic operator is just like an analytic function, except rather than having a sum of infinitely many monomials, right? Just like analytic function, but rather than true monomials, which were our analytic function monomials, something like t minus t naught to the k over k factorial or whatever, those are monomials. Rather than the true monomials, we have derived monomials of some degree. This is a footnote. That's not degree k cubed. So that's a footnote right there. But we're just going to add infinitely many of these monomials of some degree. And that's called an analytic operator. Technically, we do require a convergence in the space of operators. This is a topic for graduate math. Okay, so just like analytic functions have a radius of convergence, these will also have a radius of convergence, and we need to require that in the space of operators here. But these are the ones we're considering, and I have a quick line that refers to that quadratic functions are in fact analytic operators, right? So if I just consider the classic, this is a quadratic functions on the real numbers. The classic quadratic functions, ax squared plus bx plus c, it's an analytic operator because n sub 2, which is the k equals 2 term, is ax squared. You can confirm that would be a bilinear operator if instead of x squared I had x and y or something like that. Bx, you can confirm that that's a linear operator, a one linear, right? One multilinear and linear are the same. And then c, which is a constant, is a zero multilinear operator, right? It has zero inputs, and it just has the constant as the output. And every other multilinear operator there is zero. So this is a nice example of an analytic operator, and these are the ones we're going to be thinking of. So that's where I stop for today. I know it's kind of intense, this whole like multilinear stuff, but it's really important. This is really gonna pave the way for a lot of future ideas that we have in this course. So thanks for sticking with me. I'll see you in class. Bye.